All right, let's start the colloquium. So today, not an unusual colloquium day, but delayed because, or earlier than normal because we have our external advisory committee visiting tomorrow and Thursday. Robert Cameron, today's speaker, is a member of that committee, but he doesn't start in that official capacity yet until tomorrow. So feel free to harass him plenty today during the colloquium. Robert got his PhD in Sydney and then did a couple of postdocs and eventually landed at the Max Planck Institute in Germany, and he's now a staff scientist there. And today he's going to talk to us about solar dynamo.
Yeah, and in particular, I'm going to discuss what we can infer about the dynamo from observations. And just as a preamble, I want to mention that the sun is a star, and in terms of being a star, its activity, whether you measure the chromospheric activity as a function of basically the rotation rate, or you measure the X-ray activity as a function of the period of the dynamo, the period essentially of the dynamo, the sun, in both cases, isn't particularly active. We have a log scale here, we have fast rotators. Sun is quite inactive. And then Sadis et al. Have argued that the sun is actually near the critical point where dynamo action ceases. So the idea is stars rotate. When they're young, they rotate fast. When they get older, they slow down. You can make a model for how slow they are, and this is the prediction in this plot. The prediction, you can then compare to the observations. You make the ratio, and you find the models work well for different type of stars until about halfway through the man-sequence lifetime when stars no longer spin down. And they argue this is because somewhere near here, the dynamo action would switch off, the magnetic field becomes extremely weak. The global scale magnetic field. So that finishes my preamble. I want to move to the sun. We have observations of the sun, resolved magnetograms for the last 40 years. From these you can make butterfly diagrams. The top is a butterfly diagram for the radial field. You can see the well-known butterfly wings. And you can see material flux, which is vectored towards the poles. We also have butterfly diagrams of the toroidal field at the solar surface. And again, we see the butterfly diagram, but we also see lots of activity emerging at high latitudes. Because this one isn't so much discussed in the literature, I thought I'd remind you how this is made. Well, it's made beginning from full disk magnetograms. You take 1 year of these, and you can make a deep magnetogram. This is a very deep magnetogram. It's 1 year average magnetogram. You can see that this has a lot of structure. It can be broken into two components essentially. One component which is axisymmetric with respect to the, symmetric with respect to the rotation axis of the sun, which goes from north to south. And this gives you a map of the radial component of the field. So you take from either, you fit this curve, and what you get is a radial field as a function of latitude and time. So for each latitude, you extract a profile of the integrated line of sight component of the field. You then have a function from one side to the other. You fit it with a cosine, and you get the radial field. In principle, and in fact, you can do the same with the asymmetric component. Because it's asymmetric, it vanishes in the middle. You fit a sine curve, and you come up with the longitudinal field. So this is the yearly averaged value of the longitudinal, the averaged phi component of the field as a function of latitude and time. And why this works is, well, if you have a symmetric component, 0, 0 on each limb, has a maximum in the middle, this is what you get from a toroidal field. If you have a toroidal field, it's positive at one limb, you get no line of sight contribution at the center of the disk, and it will be negative at the other limb. So these observations, again, butterfly maps of the two components of the field, the radial toroidal field and the toroidal field. So we can measure both the components of the dynamo. Remember, a dynamo is a loop where you go toroidal, 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 over and over again ad infinitum, or at least until the star ages and other things become more complicated. Okay, this is at the surface. Why is there a toroidal field at the surface? Well, there's a toroidal field at the surface because we have flux emergence. At all times, all latitudes, we have flux popping up through the solar surface. To the extent that this obeys Hale's law, we have a systematic component of the horizontal field. So for instance, in this case, the flux goes, this loop has the same sign, the flux has the same orientation, and at the other limb, the same orientation gives you a negative component to the line of sight field. And this is simply because flux tubes don't instantly go from beneath the surface to above the surface, they pass through the surface. And you can put in the numbers for the rise speeds, you can put in the numbers for the observed rates at which flux emerge, and numerically it works out to give you the images I showed before. Of course, this implies we have ephemeral regions emerging at high latitudes before the cycles begin, but this we've already observed. This was observed by Karen Harvey in 1994. Before a cycle begins, you have an extended cycle where ephemeral regions emerge at high latitudes. And these ephemeral regions imprint themselves as they're emerging from the surface in the B5 component we observe. So here are the observations again. I really like the observations. Yearly averaged observations. These ones are from Mount Wilcox, from the Wilcox Solar Observatory, and these are from the Kitt Peak program, where I've remapped these ones to have the same resolution as the WSO ones. So we've got both components of the field, and if I change the saturation, you can see now how nicely these begin at high latitudes and then propagate equatorward. So this is the extended cycle, and this is the usual part of the butterfly diagram, which you can see, for example, here in the radial field. And if you look at this for long enough, you come to the conclusions that the dynamo problem is, in some sense, very simple. At times when the polar fields are maximum, so when the toroidal field is maximum, the whole field in the hemisphere is concentrated at the pole. So you have more or less one sign radial field concentrated entirely at the pole. The other hemisphere will have the opposite polarity, also concentrated. And when you go from one cycle to the next, the polarity reverses from negative to positive, or from positive to negative. If you look at the toroidal field, we also have more or less the same. When the toroidal field is maximum, so this is when the activity is maxima, we have the toroidal field in each hemisphere being of one sign. From cycle to cycle, it switches sign. Of course, it's the other sign in the opposite hemisphere. Okay, and this simplicity is what makes it possible for me to make my further conclusions. I just want to mention, I cannot tell you why it's so simple, but I don't think it's surprising either. So dynamo is a competition between inductive effects, which scale like UL, and diffusive effects, which scale like eta. So if we're near a point where the dynamo is switching off and our velocity field has a significant component which is global, then this L, you probably favor the largest L you can, which would be a global mode. This is, of course, not proven. It's just, suggested as a reason for why we have this simple structure. Things get even better if we go beneath the surface. We have results from heliososmology. And if you look at this, what you again notice is, so near the equator, and at each latitude, the variations, so here you see some variation, but the variation is all up in this little bit here. Almost all the variation is in the latitudinal direction, and we only have a little bit of variation in the radial direction. Important, however, is the near-surface shear layer, which is this rather rapid near-surface variation. And this simple structure, combined with the simplicity of the field, and so that it reverses the toroidal field from one cycle to the next in each hemisphere, motivates us to consider how do we change the total amount of flux in each hemisphere, toroidal flux beneath the surface in each hemisphere. And this problem turns out to be rather trivial to do because of the simplicity of the velocity field. So because the differential rotation was almost constant on radii, in particular near the equator, we can move into a frame of reference which is co-rotating with the rotation of the sun at the equator. Then we begin with the induction equation, and we're going to consider the net toroidal field in each hemisphere. So the flux inside this, the flux passing through this area, and this, using Stokes' theorem, you can convert to a line integral. And you have to evaluate this quantity. You have a quantity from the small scale diffusivity. This is negligibly small. You have the small scale effects and then the large scale velocity effects. I'm going to consider this term, the effect of the large scale. I can ignore the only effect of the small scale which survives is the diffusive effect. And this is because beneath the tachocline, I place this contour sufficiently beneath the tachocline that it's not affected by the 11-year cycle. Along this one, we've got an axis of symmetry of the system. So the alpha effect, for example, the kinetic alpha effect of these is expected to vanish. And this axis is again an axis of the system, and the only term which should survive from here is again this turbulent diffusivity. I ignore this effect, which is considered in this paper, and mainly what it does is it affects the phasing. It introduces a phase shift. But the real term which causes the flux to change from one cycle to the next is this one, the surface integral of the large scale U cross B. Well, as I said a moment ago, I'm in a frame of reference system which is co-rotating with A, with the equator. So there's no large scale U phi along this one, and therefore the integrand vanishes along A. The integrand vanishes along B because I'm beneath the base of the convection zone sufficiently far so that I don't have any solar cycle related magnetic field there. The integral along C vanishes because it's an axis of the system, so there is no toroidal motion along A. It would be a bad singularity of the velocity field if there was. So the only contribution comes from D. And the nice thing about this contribution from D is everything in here is observable. It's observable, and the observations look like this. It's just our typical magnetic butterfly diagram for the magnetic BR. The differential rotation looks like this. We're in a coordinate system, again, rotating with the equator, so it vanishes at the equator. You can look at the integrand of this. The integrand looks like this. And remember, from the northern hemisphere, to calculate the net toroidal flux produced in the northern hemisphere, we integrate from 0 to 1. And the southern hemisphere, we would integrate from, no, actually, we integrate from the pole to the equator. So we integrate from the pole to the equator, from 1 to 0, to get the sign correct. And this immediately tells you that the contribution to the strength, to the amount of subsurface toroidal field comes from the poles. It's almost all coming from the poles. And this is why the polar fields are a good predictor for the next cycle. So the conclusions from this first part, the toroidal field we observe at the surface is due to flux emergence. And the butterfly maps of the toroidal field show the cycles, the extended solar cycles beginning with the poles. This toroidal field is generated by toroidal field at the surface, which gets wound up. We can go, of course, this is nice, but I want to go a little bit further. Okay, you can ask a question.
When you do a line integral, why don't you take the radial components all the way to the core? So why do you stop it just below the line?
So it's a
circular sector instead of
yeah, so you'd have to make a few additional arguments, but you could do so. But you can choose whatever contour you want. I chose the contour I like. I'm not saying it's the only contour which you can make interesting arguments with. I'll do another contour in a minute. Apart from the, okay, so I want to go further. So what do? Well, I say, apart from, we saw this before, the near surface shear layer, the rotation rate is almost independent of the radius. We have the induction equation. I want to integrate this induction equation, the phi component, over the radius. So I can get the latitudinal dependence of where that toroidal flux is stored. So we saw how much was generated before. Now I want to know its latitudinal structure. So I introduce this variable, which is just the subsurface toroidal flux density. And the induction equation breaks up to look like this. You've got terms which are source terms for the toroidal field. This is the winding up of the toroidal field due to the near surface shear layer or due to the latitudinal differential rotation. And you have two transport terms. So this would be the transport by meridional circulation, by turbulent pumping, by whatever combination of turbulent forces you want. This is a diffusive term, again, due to the turbulence. So these are part of an infinite expansion of the turbulent EMF. We have truncated it at second order and chosen the simplest form for the function form for the velocity, and the diffusivity is constant. And if you look at this equation, well, we have observations of the surface magnetic field, we have observations of the differential rotation, we have observations, this term's observable as well. This term, we don't know V phi, and we don't know the value of eta. But we can plug this into here and see how we do. And I did this. I plugged the observed magnetograms into the above the equation from the previous paper. I use these values for the 2 free parameters, and this is what I get out, which compares quite reasonably with the WSO observations. You'll notice this cycle is very weak, but that's because the peak NSO observations, the first ones, also had very weak polar fields. It's, this is an artifact of using observations which have changed in quality as a function of time. If I want to do more, then I have to look at how the toroidal field evolves. And the toroidal field, I told you, is a radial field poking out through the surface of the sun. This field, again, changes cyclically, 11 years to 11 years. At minima, it's all concentrated near the poles. So I do the same as I did for the toroidal field, and I ask myself, how do I go from here, at minimum where it's all concentrated at the poles, to the next cycle where it's all concentrated at the poles, but it's changed sign. Again, I'm going to apply Stokes' theorem. In this case, I apply Stokes' theorem to the surface. So my surface is the whole photosphere in the northern hemisphere. And the line, my line integral, is the equator at the photosphere. I then can calculate the time rate from the induction equation, the time rate of change of the total flux for the northern hemisphere. It turns out to be this. Evaluated at the equator, the velocity carrying the field horizontally across the equator, or horizontal field rising or emerging across the equator. What does this look like if I look at the observations? If I look at the observations, this first term is the turbulent transport of radial field by the turbulent motions, so turbulent diffusivity essentially, across the equator. And this is how the surface flux transport models have always transported flux across the equator. There's a second term, which is emergence near the equator, or in particular, most impressively, across the equator. And so here you have an emergence where from one Carrington rotation to the next, this large active region has emerged across the equator. And this, of course, injects a substantial amount of negative flux, net flux, into the southern hemisphere and an equal amount of positive net flux into the northern hemisphere. And eventually this flux will get carried by the meridional motions to the poles. But in terms of this integral, it's this emergence which matters. And you should understand how important events like this are. This is because the polar fields at the end of the cycle, which is so important for generating the next cycle, are about the flux of one active region. If this active region, the whole flux goes from, the whole positive flux went to the northern and the whole negative flux went to the southern poles, this would be more than the flux of a typical cycle. So events like this, or even a little bit away from the equator, contribute to the variability from cycle to cycle of the polar fields, and about 30% per cycle. I'm going to skip discussing the surface flux transport model here, but if you actually want to follow the evolution, and people have since the 80s and maybe a little bit before, of the magnetic elements to the pole, you use the surface flux transport model, which basically says the flux is carried polewards by meridional flow after emergence. It doesn't say anything about emergence, so there's this source term, but after emergence, meridional flow, diffusion. And if you do it in 2D, there's also differential rotation you have to take into account. In any case, this then leads us to the updated Babcock-Leighton model. So there's a typo or a small error in the original Babcock-Leighton model. It's not present in this one. And we've added noise in the form of just white noise in the source term for the surface flux transport, so in the emergence process. So this is the equation from the previous page, these two, describing the surface. And these ones are the equations I showed you earlier. And they're linked via this term. And this is the most important one, which relates the subsurface toroidal field and says it can emerge to the surface. And when it emerges to the surface, it's acted on by the Coriolis force in some manner, which we may or may not get to, which then produces a systematic tilt, which is known as Joyce law. So this embodies Joyce law and links the subsurface equation to the subsurface evolution. And you can try this model and see how it looks in terms of its variability. And here, for example, I show the observations of the sunspot number for the last 400 years and the reconstructed sunspot number from cosmogenic isotopes for the last 10,000 years. These are observations, and these are the models. And statistic, of course, these are random realizations. So you don't expect them to be one-to-one comparable, but you expect them to have similar statistical properties, which they do. Which is a little bit surprising because you can't really think I've got everything correct in my Dynamo model. So why do I get the correct statistical properties? Well, it turns out these statistical properties are completely generic. They're generic for any alpha omega type dynamo which is near the bifurcation point at which dynamo action switches on. So dynamo action for a alpha omega dynamo switches on in terms of a Hopf bifurcation. Hopf bifurcation lead to nice regular little limit cycles. We're not out here, which is the chaotic regime. The observations from the stellar side tell us we're near this point. Of course, we don't have the nice little limit cycles on the sun because we have noise. And so if you have noise, you take your equation for the Hopf bifurcation and you add a noise term. And when you do this, you find the same statistical properties as we found in our Dynamo model, in our updated Babcock-Leighton Dynamo model, and in the observations. And you can look at the power spectra and the periodicities present. In this case, in green and blue are the observations, so 400 years, 10,000 years. The black is the median from 1,000 realizations of the noisy normal form model, and the grey shaded region shows you the 25% confidence intervals. The bottom panel is the same, except I've put in the Babcock-Leighton Dynamo model instead of the noisy form model. But they both give us the same result, essentially, because the behavior is completely generic. It's determined by the noisy form. And this is just one realization to show you, yeah, sure, you can. So some people talk about this 2,000-year periodicity. You can find many, many cases in the random simulations which look completely identical. This brings me to my second set of conclusions. And again, this one, I can't emphasize, how important I think this is. 4 solar cycles of observations at the surface of the toroidal and poloidal field. The poloidal field is a field which we know is responsible for generating net toroidal flux in each hemisphere. And the toroidal field is coming from flux emergence, and therefore it's the closest we can get to visualizing the subsurface field. They both have extremely simple structures when they're maximum. You know, this dynamo is operating in turbulence. The convection zone is turbulent. These parameters, your mean field parameters, vary, and they introduce about 30% variation per cycle. This I'm not going to discuss. I didn't discuss it, didn't have time. And the updated Babcock-Latin model shows you how all this fits together. But in particular, once you've got these two, once you've got observations of the toroidal and toroidal field, I think understanding the dynamo is much, much simpler. Okay, so this was all about the 11-year cycle. The cycle varies on shorter time scales, and these are called, for example, quasi-biennial oscillations, but they have other names. And Roger Ulrich likes to talk about ripples. These are ripples. The Wang and Shiri talk about polar plumes. And what I want to show here is these poleward plumes and the near-surface shear layer, and what produces quasi-biennial oscillations. So this is the observations I showed you before, yearly averages of the radial field and the toroidal field. Instead of using yearly averages to study the quasi-biennial oscillations, you need to really switch to a 3-month averaging. So you have a high level of noise, but on the other hand, you resolve the features you're interested in studying, which turns out to be a good idea. You can see here for a start the plumes or ripples. And these are, as I explained before, individual large active regions can have various tilts. And this was studied first by Wang and Shiri, but also later by McKay and others. And what happens is you get an emergence of a large tilted dipole region. In this case, the red on top, blue below. And then this gets carried by the meridional flow towards the poles. The red arrives first, then the blue, and then this can happen again and again. This is more interesting. Why are we seeing periods with strong toroidal flux emergence and periods when there's very little within a cycle? Well, to bring this out, I filtered out everything with a period of beyond 5.5 years, so we can see much better the structures. So this is the radial field. This is the filtered radial field, so you can see very nicely the plumes, or the ripples.
Explain again how you filter.
I just filtered out with a low frequency filter everything with a period greater than 5.5 years, so greater than half a cycle. These have a period of about 2 years. They're well beneath my cutoff. I decreased the filter to 3 years. I still see these same features. These features aren't coming from my filter. And this is the toroidal field. And you can again see this a mess. So what to do? Well, we have the equation for the evolution of the subsurface toroidal field from the Babcock-Latin model. And it consists of 4 terms: winding up of the field due to the near-surface shear layer, winding up due to latitudinal shear, transport due to pumping, and transport due to turbulent diffusion. For yearly timescales, on 11-year timescales, this moves the toroidal flux from, say, 38 degrees to 8 degrees. But on yearly timescales, about 2 degrees per year, this isn't going to move it within one of our pixels. Our pixels, remember, are quite large. These were quite low resolution images. So we can forget this one. Also, the latitudinal, our images were not so rough, so we can also ignore this term. We only have these 2 terms left. So, and these 2 terms, well, we know everything which goes into making them. So we can actually make an image of them. This is an image of the generation of toroidal field as a function of latitude due to the near-surface shear layer. So it's the near-surface shear layer acting on the radial field, and this is the original image, and this is when I filter. I also apodize to get rid of any effect of the edges, but the apodization, like the choice of the filtering length, makes no difference. And this is due to the toroidal field generated by the winding up of the field due to the latitudinal shear. And then I calculate the cross covariance of the generation of the subsurface toroidal field with the observed toroidal field at the surface. Yeah? So I see the field at the surface. It was my map of the toroidal field. I know the rate at which it's being generated beneath the surface due to either the near-surface shear layer or due to the latitudinal shear. And so I just make a cross covariance between those 2 quantities, and then I integrate it over the activity belt. So in this case, from minus 30 to plus 30 degrees. And that's what these are. This one is I take the total generation. So the generation by both types of radial and latitudinal shear. And what I find is this peak, these 2 peaks, positive and negative, mainly coming from the near-surface shear layer. And this is offset with about a 90 degrees phase shift. Yeah. So the generation, this term, the generation of toroidal flux in the subsurface is quickly followed by the appearance of toroidal field at the surface. So the toroidal field generated by the near-surface shear layer modulates, first positive and then negative, the field we observe emerging at the surface. So to understand what's happening a little bit more, to make it a little bit easier for you, let's just concentrate on one pair. So one plume goes through, first the negative flux and then the positive flux. Let's see what's happening. Well, first of all, this negative flux goes through. Okay, it's positive flux. Positive flux goes through. It's directed upwards. It gets sheared, because I'm looking in this hemisphere, yeah. This positive blue goes through. This is now a field line penetrating the surface. Here's my blue patch at the surface. This gets sheared by the near-surface shear layer and produces negative toroidal field. This negative toroidal field weakens the positive toroidal field which was there, and you get a reduction in the emergence rate. This is followed by the passage of a negative radial field being carried polewards. It's negative. It's acted on by the near-surface shear layer. It creates positive toroidal field, which strengthens the pre-existing field, and so we get enhanced emergences again. So my conclusions to this part are that the poleward plumes of the surface radial flux strongly modulate the emergence rate. This explains the QBOs. It modulates them because the near-surface shear layer acting on the radial field is generating toroidal field. And that toroidal field almost immediately either increases or decreases the emergence rate. And this tells me that the flux is not emerging from the base of the convection zone, but is coming from somewhere quite close to the surface. This is, of course, consistent with a whole bunch of other work on other stars.
And the sun, the beam frequency shifts have been localized to the surface regions.
Yeah, only sun. Yeah, okay, but this, yeah, the sun is a little bit more difficult. That's a little bit less ambiguous, more ambiguous. Okay, and so this brings me to question time. Do people have questions, comments, bits they disagree with?
I'm sure there's some questions. Matthias?
So how strong is the field modulation you get in these videos? That might allow you to also estimate maybe a little bit how strong does the field has to be to begin with to be able to form the active regions. And so on a very short time, so you can modulate and switch it on and off.
So yes, you can see these are large modulations. And if you look at the sunspot numbers in each hemisphere, you also have a large modulation. It's stronger here because you avoid the overlapping. So these weakening and strengthening part of the overlap as they propagate polewards. It's a strong modulation. And yes, you can do more along these lines. Axel?
Would you go as far as saying that the dynamo itself could come from the near-surface shear layer?
Yeah, so what we know is, so this is a modulation. It's not enough to explain the equatorward propagation of the dynamo. And in particular, if you look, so there's several reasons for this. We can tell how much flux is generated by the near-surface shear layer. It's it's given here, and this is large, but it tends to come in patches which are positive and negative. And if you integrate this over a yearly time, you find it's too weak to explain the equatorward propagation by about a factor of 4 or 5. In addition, most of the toroidal flux, I think we need most of this, is actually produced at about 55 degrees latitude, and you need something to get it poleward. You notice in my model, you still need about a factor of 4 or 5 to advect the material equatorward. So you need some type of velocity.
Now, I think I understand why you only have 4 cycles, because only for that time span you have observations of the surface field, of the kind of quality that you need. Nevertheless, is there any way that you could draw information of the observed butterfly diagrams and distributions before that would help you to solidify these conclusions?
Yeah, so in principle, so these 2-year the quasi-biennial oscillations are seen in the sunspot number. So you could certainly go back and you will see the quasi-biennials present. The interpretation is a little bit more difficult because you need to know the orientation of the plume, if it's blue-red or red-blue. But maybe you could do something. But on the other hand, I think this is significantly beyond the noise level. I agree, it would be nice to have observations from before.
So how does you the evolution? I mean, if the dynamo is going to shut down at some point in the future,
But
we're
no, no.
close to that edge, how will that look like?
No. So this isn't my topic, but just let me, say it's not clear to me. Yeah, it's not clear to me how easy it is to go across that barrier. So the point is, when you reach this stage, as you go further, your dynamo gets weaker and weaker and weaker very quickly. Its effect on the angular momentum evolution becomes extremely weak very quickly. So it's not clear to me you ever really switch this off. You can just get weaker and weaker and weaker. The dynamo activity gets lower and lower and lower, and therefore its effect on the rotation rate gets less and less and less, until eventually still evolution kicks in again at some point. The sun expands.
So what we will, so my question is, under this assumption that this is correct.
Yes,
the assumption that this is correct and we're in that limiting.
Yeah, but no, this limiting thing is a limiting thing. The axis here is rotation is h, yeah, and the physics is determined by the rotation rate. And what this tells you is after a certain h, you no longer have rotational evolution because your field is too weak. So the sun will stay as it is, a little bit weaker for the next.
Oh, I see what you mean.
Yeah, so it's not, I don't see any strong reason for thinking you jump across from solar to anti-solar differential rotation, for example. You just get weaker and weaker and weaker and weaker dynamo evolution. Your dynamo spins a little bit weaker and weaker at the time, but never crosses.
But the differential rotation is stronger for anti-solar.
Yeah, but the question is, how do you get from solar to anti-solar? And according to this type of analysis, it's not going to be easy because the angular momentum is driven by the large-scale magnetic field. And so if the large-scale magnetic field disappears, the angular momentum changes, disappear. So you begin solar-like, your dynamo action becomes a little bit weaker, you rotate a little bit slower, but not as slow as if it was up. You reach the point where we are now, halfway through the main sequence lifetime. After this, the angular momentum evolution, large scale, stays the same. This is what this grey patch basically is. The star ceases to evolve. It stays like this for the next 4 billion years, except for, it gets a little bit bigger due to still evolution.
If they remain fast.
Yeah, but how do you get slower? If you switch off the large-scale magnetic field, you switch off the angular momentum braking.
Right, so basically this means that the kind of activity that we're seeing right now is for your purposes what is going to be for a long time.
Yeah. And in fact, for a long time here probably means much longer than, we're interested in, yeah. Yeah.
Billions of years.
Yeah.
So
Beyond my interest.
one data point that I can provide is the Alpha Centauri. A billion years older than the sun, and its X-ray cycle has like a third of the amplitude of the solar system. That gives you an idea of how quickly the amplitude goes.
Yeah, so the argument essentially is, this is the generic place. Stars end up getting closer and closer to this point, but never reaching it. And as soon as you're within 4.5 billion years, your dynamo is going to look like this. You'll have more than minima. It will be rather boring, but well, it's the star we have. It is.
If that is the case, shouldn't we then expect to see a lot of stars which have very solar-like activity by now? My impression is when people look at it, that that's not necessarily the case, but then we just have to look at the right stars.
Yes, so these stars, of course, have weak cycles and there's observer biases. But I'm talking more about the sun. And
Yes, one is we don't have a lot of observations. Sunlight started with slow rotation rates where this type of parameter regime might exist. And what the speaker told us there's two free parameters in this model, how they depend on molten sand.
Yeah. But this behavior, I think, is generic beyond those two free parameters. Mikhail?
Glad to see that this is not another doomsday scenario. But here comes my usual question. Why 11 years?
This is explain. Okay, yeah. Yeah, so this comes back to where these two free parameters are coming from. So usually people ask me after giving the first part of the talk, where is the toroidal flux in the convection zone, which I could never answer before. Now I can answer this, of course people want a different question. Fine. You've got two free parameters. Oh. One of them is the subsurface return flow, this one. This one has to be somewhere between 1 and 3 for you to get a 11-year period. And this other one, the diffusivity, has to be somewhere in the range of what the simulations predict. This one, the return flow, I'm not even sure what this is. It could be the return meridional flow, but I'm skeptical. It could be some type of magnetic pumping. My guess would be magnetic pumping, and all I can tell you, yeah. So if I had a different value for the parameter here, the solar cycle would have been 15 years, and you would have asked me why it's 15. If I had a different value, it might have been 8 years, and you would say why 8. It depends upon this process. The whatever is carrying the field beneath the surface towards the equator. I can guess what this is, but not in this talk.
So can you go back to the realization, like the sample realizations that you were showing, the slide that has the 3? Yeah. So I was curious about when you look at 10,000 years, the one that is the Dynamo simulation has peaks, like grand maxima, that are significantly larger than when you get from the cosmic rays. And I was wondering.
This is the so the cosmic rays come with air bars, and I've excluded the air bars, but these peaks could well be within the air bars.
Okay.
I just took the mean value.
It's just that.
Larger than the noisy normal as well.
So the noisy normal form is more compact, to say.
Okay, so I just measured the number of Maunder minima, and this turns out to be the same between the two. There's certainly, this, if you don't, even if you take the mean values for this, you have negative values for the sunspot number. So this should be, isn't perfect.
Yeah, I mean, I'm really genuinely curious if there is something that might just prevent the sun from, like, something that is not in the model, of course, because the model is not.
Yeah, so I can't answer that question because this record is somewhat sketchy. Certainly, there can be more physics, and these limits may not be realistic.
Yeah, so you added some noise term to your model, and it's related to the cross-equator flux emergence.
It's actually related to the tilt in the scatter and the tilt angle. It's the most dramatic examples are these ones, and the ones which have largest effect are these ones which emerge across the equator. But if I have something, if this emerged just a little bit further northward, it still would have had an impact, because the random motions would have carried more of the black across the equator. So it's not just the cross-equatorial ones, it's all the highly tilted ones. Yeah.
So I wanted you to comment in general on the exercise of predicting solar cycle amplitude.
Yeah, so if predicting beyond 1 year, you're going to have extremely large air bars. Prediction from towards the end of a cycle, it's a question of how well we can predict these polar fields. And they will always come with error bars because you've got this 30% plus or minus, that's at 1 sigma level. So you do predictions with error bars for not more than, say, half a cycle, and that's what you can do. The error bars are large, and of course, this ignores, I mentioned this for Matsumi, this ignores the fact that what you're usually interested in predicting is not something which is smooth, but something which includes the quasi-biennial oscillations, or whatever you call them, which will have additional noise. So noisy, but if you make a prediction and you give the error bars, sure, why not? Large error bars.
Anything else?
Now there are quasi-biennial oscillations in the Earth's atmosphere. The only thing that has been found solidly where there is a clear
Correlation. Okay.
relationship to the solar cycle are quasi-biennial oscillations in the Earth's atmosphere. Do these have anything to do with one another?
Yeah, so I think I'm interested in the sun, yeah? But I think the observation says that the quasi-biennial oscillations are seen in the geomagnetic field, for example, and from there I can imagine in the modulation of cosmic rays, but that's not my topic. I like the sun.
We should discuss this further.
Last question, Ricky.
So everything hinges on the mean field separation, big U and little u.
And no. So this part, for example, was all observations. There's no mean field separation in here at all. So part 3,
All
the
of your integrals take it for granted. There's big U and little u. Isn't it implicit in there?
let me see. Yeah. Okay. So yes. Okay. In some sense, yeah.
Right. So I mean, there's a little bit of debate whether that assumption is valid. Would you comment on that, or would you
Yeah,
think that
so-
the successes of this model would be
So
that it works?
this I take to imply that the quasi-biennial oscillation is associated with the winding up due to the radial differential rotation. I think that's the way you get this plot. It doesn't. I don't think this requires very much from the separation of scale. This is just no.
I mean, sometimes, I mean, you can always separate it out into big and little u. I think most of the uncertainty in the discussion comes from this when you try to parameterize the correlation of the different u's and u. But Robert didn't do any of that. So, but you can always draw a line somewhere and separate your fields into a large and a small scale component. There's nothing wrong with that.
Okay, and since that was the last question.
Let's thank Robert again.